how much you work?
Sure work. So it's a pleasure to me to introduce Professor V M Braun from University of Regensburg. He's one of the great professors of quantum chromodynamics that we have now. He's 40 years or 50 years of UCB, I don't know how many years he was working on this subject, on many issues from normal BFK, higher twist calculations, and there's a huge amount of processes, a huge amount of work that he has done. Impossible to listen to me. So we have a pleasure to have him here. The occasion, as I said, is this workshop we are having these days about this HEI staff exchange collaboration. The director is Francesco Aprilia. And so we are connected also with the University of Turin, NICEP, Paris, and Porto, and I hope not to forget anyone, and the city perhaps. So the subject is conformal symmetry strong interactions, and so I'll leave the word to you.
Okay. Thank you very much for the invitation. And to start with, I have to apologize to our friends from Terina, because I have given just the same talk more or less in Terina a very short time ago, and I was just lazy, to do something else. And also, the new results do not come so often. I couldn't change it too much. So So the point of this talk is essentially that unitary scale invariant generalizable field theory possess some additional symmetry, which might be quite miraculous. So why do they possess additional symmetry? But they possess inversion symmetry, which is this symmetry to inversion transformation invented actually by a school teacher, Magnus, in 1831. And at first sight, in QCD, you would ask that in QCD, that transformation just it mixes small distances with large distances, so it transforms the asymptotically free region to the confinement region. So what can it have to do with the real QCD? But as we see that there is some use, and the use of for this symmetries. This is what we will be talking about. So. This was already yesterday here mentioned. I have the same picture. So if you have a conformal symmetry, so you have a conformal symmetry in field theory, so the conformal field theory has the following very important property, that 2-point functions and also 3-point functions in this series are known exactly up to some constants, where this deltas are scaling anomalous dimensions, are scaling the dimensions of the operators, and the constant in perturbation theory can be perturbatively coupled. So this actually almost can be taken as a definition of a conformal field theory. The theory which is conformal has these properties. Alternatively, the thing that conformal theory allows is the following: if you do the operator product expansion, and you have a contribution of a certain operator in this operator product expansion, and you in principle have also contributions of operators that are given by derivatives of this operator that we have here. And the statement is that all these coefficients of the operators with derivatives can be related to the coefficients of operator without derivative by symmetry transformation. So that is a very important property. This I will have some examples of where it's important. This example refers to the situation that the point is that matrix elements of some of these operators vanish on free quarks. And therefore, the usual methods of calculation of the coefficient functions of the operator process simply don't work. We have to invent something more complicated, and conformal symmetry solve it in a very elegant way. I will give such an example later. So, well, what really happens in QCD, of course, is that QCD Lagrangian formally, at least without gauge fixing, is conformally invariant. but the symmetry, of course, broken by quantum correction. And an old observation or an old idea you can treat it both way that for a generic quantity involving some flat scale in perturbation theory, the answer for this quantity can be written as the result in some conformal field theory plus terms proportional to the beta function and multiplied by some other series in alpha s. And if you want to do it systematically, the question immediately arises, so what is this Q in the conformal field theory? So what is the conformal precise? What is the precise in the conformal field theory, which this quantity is about? For quite some time, actually, from this idea was very old. It's like coming from like 80 probably. People were just basically waving hands and saying that you just put the beta function in QCD to 0 by hand. This, of course, you cannot do systematically because you have to change the theory. You can do it in one group, but you can do it systematically. You change the theory, and you have to define this conformal theory specifically. And in principle, the general idea is quite clear. You can consider, you can just embed your QCD in a more general theory that has conformal theory. The case that you'll here know is that this n equal to 4 supersymmetric theory that adding a lot of additional fields, you can make the theory super conformal invariant. And this is just an example of such a situation. But the problem is there how you go back such a conformal theory to the real QCD, because in n equal to 4, this is a lot of, the distance is very large. You have to get rid of all these additional fields. And the proposal that we had, and we proceed now systematically with this, is to consider the QCD in a Wilson-Fisher critical point in the non-integer number of dimensions. So this can be viewed in the following way, that you consider a theory with two coupling constants. So one coupling constant is just the usual coupling constant, and another coupling constant, which is also considered determined, is a deviation of d from 4. So the theory has two coupling constants, so this alpha s and 4 minus d, and in the plane of this coupling constant, there is a critical line on which the theory is conformal. So this way of realization of conformal symmetry is very close to what is done, of course, in condensed matter physics, when conformal field theory arises in the points of phase transitions. So this is different from n equal to 4 in that it's just conformal theory is valid only for a particular value of the coupling or for a particular value of epsilon for fixed coupling. There are subtleties to prove that this theory is conformal. For example, because this theory is actually rather pathological, it is not unitary. So we consider this, and I think we can prove that this theory is conformal. There are some subtleties, and this is not what I'm going to talk about. This requires what I want to say, that requires actually some thinking and some special proof that it's conformal. So a lot of examples that I will be considered refer to actually to the separation of longitudinal and transverse distances, and from group theory point of view, which just means that we can reduce the full conformal group to a certain subgroup, which is called the collinear subgroup. And that corresponds to the basically to the selection of three transformations. You have a line along which the particles propagate, and you consider the conformal transformation essentially along this line. You have special conformal transformation along this line, you have translation along this line, and you have a dilatation transformation, scale transformation. So this is the group transformation where A, B, C, and D in this case are real numbers, not complex numbers. And so this is a SL2R group actually, and some combinations of this transformation can be produced to reduce the algebra of this group to the standard form. And this SL2R algebra, so this is minuses, plus, and then zero, some combinations of these three transformations. This is a standard SU for algebra, which satisfies this commutation relations. So this yacht here is a quantity which is called conformal spin, which is a half of the dimension, the canonical dimension of the field and the spin, and the spin projection actually on this light on direction. And if you compare it to the usual O3 commutation relation, you will find that there's some side difference. And the reason to the usual SU3, you can naively think about it in the following way. So the usual spin is just a unit vector which lives on a unit sphere, and it is quantized. And in this case, this is a non-complex spin which lives on the hyperboloid is also quantized. Also quantized, so the split projection, so to say, of the spin is always bigger than the spin itself. But otherwise, the properties of this subgroup are very close to the usual rotations, and the usefulness of the techniques that I'll be talking about, to a large extent, are related to the fact that there is a lot of mathematical results for the representations of the SL2R group, which can be used with, to obtain the result. This is, of course, I will not be talking about, but technically, many things that we're talking about are related to this specific techniques that you can use for this group. So now, so this what it actually does is very introductory transparency. So what this separation of this subgroup does is essentially very similar to what you do in quantum mechanics, in the introductory quantum mechanics course, where you have a hydrogen atom and you solve it by observing that because of rotational symmetry, the solution of the Schrödinger equation can be written as a spherical harmonics times some function of the radius. So it gives you a separation of angular dependence and the distance. And the spherical harmonics are, of course, eigenfunctions of the quadratic Casimir operator of the rotation group, L squared. And then for R, you have this one-dimensional Schrödinger equation. And so in high energy symmetry, so this classification according to SL2R, it essentially serves the same purpose. It just serves to separate not rotation and the coordinates, but longitudinal with transverse dependence. So longitudinal dependence can be included for the wave functions in terms of the eigenfunctions for the corresponding Casimir operator, and transverse dependence corresponds to the realization group equation for the operators that appear in this way. So this is very old stuff. It is summarized in our old report 20 years ago. So I will be talking about something which came after that. So now a little bit more specific. So what is actually QCD in non-integer number of dimensions? So I consider now that the gauge fixed QCD Lagrangian because we're going to do perturbation theory. And then we just go to renormalize it, making the renormalization in a standard way, where the Z factors are defined using minimum subtraction. That's very important. This normalization scheme is used. And so that's a standard procedure for normal QCD. And the only thing that we don't do is a standard case, after we subtract this constant, we do not send epsilon to 0, we keep it finite. So the results will depend on epsilon, and these are the results in the D-dimensional QCD. So now what happens if you have dilatation, if you have this action in this D-dimensional QCD, and you can consider variation of the action due to the dilatation transformation. So this is the or you consider variation of this action with respect to the conformal transformation. And what you see immediately that the under the dilatation transformation, the variation of the action is proportional to epsilon. So in 4 dimensions, it's invariant under dilatation as we know. But for the conformal transformation, the variation of the action, even in dimension 4, has an extra term which doesn't vanish. It's just proportional to epsilon. But the point is that this extra term, which is this extra operator which appears here, it is actually can be written as a Berenstain transformation of this type. So in reality, it will disappear if you go to correlation function of gauge invariant operator. But the difference with scalar field theories, the conformal symmetry of QCD even at the tree level is not valid for green function. It is only can speak about conformal invariance for correlation function of gauge invariant operators. Otherwise, the conformal symmetry is just broken in a straightforward way. So now the main tool that you do in this kind of calculation, so what in all symmetries, you usually say that your symmetries you can view them as change of variables in the path integral. And so if you consider, for example, correlation function of two operators, and if you make this change of variable, then what can happen that you can have transformations of the operators, but in principle you have also the pieces from the transformation of the action. So if you have canonical, if you have standard Poincare symmetries like translation invariance or angular momentum, then the action is of course strictly invariant, and then this contribution is just X. So then you just have this sum is essentially of all the variables has to be zero, and this just gives you a usual symmetry state. And for the dilatations and for the special conformal transformation, the action is not invariant, so one has to calculate this additional term and to see what this term actually gives you. In the case of the dilatations, this is exactly what is being done in other language by the randomization group, what we call evolution equation or randomization group equation. So what happens for the dilatations is that all these contributions can be included in the modification of the generators of, I'm speaking now about the SL2 subgroup in such a way that the scaling dimension of the fields will be modified by the scaling anomalous dimension. This is what will happen. This can be shown. For K-mu, the situation is more subtle. Actually, if you find operators with fixed, well, this is not precise. If you find operators with fixed scaling dimensions, then also the same thing happens. You will only have this change of the scaling dimension by the anomalous dimension. But if you don't have solutions of randomization group equations, but you just have some randomization group equation applied to some matrices of mixing operators or some lateral operators, then the point is that in addition to this change of scaling dimension, there could be some extra terms that do not contradict the algebra of the conformal group. And from technical point of view, these are really the most important pieces that you have to calculate. I will just give you an example. So so that means that basically this generates a conformal transformation corrections. So if you go to this light ray operator representation, I think here you know what is a light ray operator. Then you can write the corrections to the generator, so this deformation of the generators in the following way. So the S minus is just a generation of translation, so it has no corrections. It is a trivial translation. S0 is a dilatation essentially. And it contains here contribution, which is an integral operator acting on the light ray operator. If you can solve this evolution equation, so eigenvalues of this H, that we usually call Hamiltonian, produce your anomalous dimensions, and that is a term which just modifies the dilatation, because the scaling anomalous dimension, which is in this S0 by the anomalous dimension. But in case of the special conformal transformation, so you have a similar term. So the role of this term is also to modify the scaling dimension appearing in S plus, but also we have some additional term, which is scheme dependent, and this has to be calculated. So, for example, on one loop level, so this H here has this form. This is a very old result, and this delta plus is what is imprecisely called conformal anomaly in the literature from time to time. This has just this form here. This is not very complicated. but has to be incorporated. It's imprecise because, so in principle, so this is a dilatation of anomaly. You can say, and this whole thing is the conformal anomaly. The point is that conformal anomaly is not directly related to the dilatation anomaly. It's a separate object, has to be separately calculated. The two-loop result, that is already quite a complicated calculation, was obtained by us some time ago, and I will show that this two-loop result is actually enough to obtain some three-loop results in the real QCD. But that expression for the two-loop anomaly are already quite complicated. So now there are many applications because of here, and I will I cannot consider all of them. So I will speak a little bit on this four applications that I shown with, you know, with this kind of sign. I will not speak about range limit. This was actually, there was a lot of discussion yesterday here, and we're actually not working on this topic. I would like to talk about complete integrability, but I will probably have no time, so I don't have any transparency. I can say a couple of words at the end. If I forget, you can ask. But I will just basically have this for examples about what can be done. So, so the one very important thing that the way how this theory is renormalized is that the Z factors which we for composite operators are sums of fewer poles times functions that don't depend on epsilon. This is the definition of the scheme, and the consequence of that the renormalization group kernels, the Hamiltonians, and the Wilson-Fisher fixed point, and in the QCD in 4 dimension have exactly the same structure. So the structure of renormalization group equation changes. In the fixed point, you don't have any beta function. At least you have this equation, and in expanded impulse of the coupling, you have these H's, which are some functions. For example, for light ray operators, there will be some integral operators acting on this light ray operators. In the QCD that we're all interested in, is the usual QCD in 4 dimensions. You will have here additional corresponding to the beta function, and by this H will be written in terms of precisely the same functions as here. So the evolution kernels for all composite operators in at least for leading twist for QCD in 4 dimension and 4 minus epsilon dimension are exactly the same. So what it means, if you maybe surprisingly, that this things have conformal symmetry, they also have conformal symmetry. And conformal symmetry means that if you have a real QCD in 4 dimension, then this renormalization group kernel in full QCD to all orders of perturbation CD has conformal SL2 invariance. So there exist 3 operators with a commutation relation of SL2R group, and this also these 3 operators commute with your renormalization group kernel. I emphasize that this is the result for the full renormalization group kernels, including all beta function coefficients in full QCD, and it's valid to all orders of perturbation here. Okay, and the reduction to 4 minus epsilon in a sense is just an intermediate step of the couple. So the point, of course, is not that QCD is conformal, but the 't Hooft-Wilton renormalization scheme, in a sense, is a conformal scheme, because it is valid for this particular scheme. But this is a scheme which we all use, minimal subtraction scheme that is all using. Important is that the subtraction kernels do not depend on epsilon. And the whole point is that we can find these operators. We can find these operators from the considering conformal model derivatives, and then this equation gives us an equation to find the renormalization group kernels to higher order in perturbation C. Let me illustrate that. So you have this symmetry generators, which you can expand in terms of the coupling. You see quantum corrections. As I said, part of these corrections are just due to modification of the scaling dimension, but there are extra ones. And then you just have this commutational relation, you systematically expand them in powers of alpha s. So leading node, you just have a standard statement that the one loop evolution equations commute with the generators of standard conformal transformations. But for example, you just go further, for example, to this three loop kernels. You have an equation that tells you that this leading order generator of the special conformal transformation is 3. So this 0 and 3, these are orders of perturbation theory, is given by this expression on the right hand side. And you can see that this expression is just one loop, two loop, one loop, and this is here is 3 loop. This is 3 loop, and this is 0 is just a first order differential operator. So what you see here is a first order differential operator. And on the right hand side, you have a function which you know from one loop and two loop calculations. So if you know these functions, you can solve this equation and you find this H3. The catch is that the solution of first order differential equation is you can get up to the solution of the homogeneous term, and if this is 0 on the right hand side. And this the additional term is the 0 is homogeneous term has to be fixed in some way, and the way to fix it is to use the result for the spectrum of this operator or for the spectrum of anomalous dimension. So what this does is produces you this full three loop randomization loop kernel with the following information. You have a result for the two loop kernel and three loop anomalous dimensions. So that's what we did some time ago for non-singular case. And it was completed the fully analytic form very recently by Sasha Manashov and Svenmo. This is one kind of application. One basically can win one order of perturbation theory, which becomes more important if you go to higher loop orders. So second example that I want to consider is example of a B meson decay. So this is nice physics situation that you have. This is like a hydrogen atom of QCD. When you just have a heavy quark and the light quark which flies around. This is just like an electron cloud in a hydrogen atom. And the difference with the hydrogen atom is that the proton is stable, but the big quark can decay due to weak interactions. And so at some point it simply rapidly disappears. It decays in the light quark in a couple of leptons, which just fly away in opposite direction. And then this light quark, which is produced by the decay of this heavy quark, it propagates through the cloud of this light antiquarks. And there is some probability that they will annihilate. And in this case, you, for example, will have a decay which produces a couple of leptons and a photon from the annihilation of this quark, which was orbiting the heavy antiquark orbiting the heavy quark in the big quark, and the light quark to produce theirs. So this object is so diagrammatically you have to consider this amplitude. And the object that this probability amplitude to find an antiquark at a given light distance from the heavy quark is we defined as a B meson distribution amplitude. So it's a matrix element of a light ray operator between one light and one heavy quark. And as always in field theory, it is actually scale dependent, and the limit of it, where heavy quark is large, heavy quark mass is very large, so it is satisfies some renormalization group equations. This renormalization group equation is also complicated, and one of them can be written. So this is just this diagram that has to be calculated. So this double dashed line at the top is the Wilson line. This is a simple calculation, and this is that was done long ago, 20 years ago, by Lange and Norbert, who found just this expression for this kernel. And actually, it is kind of non-standard form because of this part, and it took actually 10 years because basically accidentally the solution of this equation was found. So the equation was written in 2003, but the solution was first found just by hand. By hands in this paper in 13, so it is 10 years. So I will show you how this why solution looks like this and how to find it in a very simple way.
What is ether?
Huh?
What is ether?
Eta is some non-perturbative function. So this is the function is written in terms of these are eigenfunctions of the evolution equations. These are eigenfunctions of the evolution equation. This is a non-perturbative part. This is a solution of optimization group equation. So this I don't write optimization group solution for this function. This is a standard form with a cusp anomalous dimension. But so this is multiplicative normalized for given S. So this is just eigenfunctions. So this of this kernel. So that's what's important. So these are eigenfunctions. This kernel are Bessel functions. I mean, usually don't find Bessel functions as eigenfunctions in QCD. So now let me show you how to get this result in a very simple way. Actually, the point here is that namely we say there is no conformal symmetry of the surrounding, and there is no conformal symmetry because there is a heavy quark which is stuck to one point in space. It's very heavy, like a proton. So there is no translation variance. Even translation variance is broken, so there is no group or subgroup at all. However, the geometry of this process, the heavy quark can be viewed as the Wilson line in a time direction or in direction of the for velocity of this quark. So the geometry is that you have this Wilson line in time direction, then a Wilson line in the light direction, and here you have a light quark. And you can show that this geometry is invariant under the special conformal transformation projected on this vector. So if the commutator of this operator is 0, it can be shown that it will be true to all loops because it is just a geometric problem. Dilatation variance is also broken. So there is nothing, almost nothing. The dilatation variance is broken by the cusp. So the commutator of the dilatation operator with this kernel is just the cusp anomalous dimension. But then, since the heavy quark essentially disappears as a dynamical variable, you have a one particle problem. And if you have an operator that commutes with your Hamiltonian, then the eigenfunctions of your Hamiltonian will be also eigenfunctions of K. Or in other way, the eigenfunction of K will automatically be eigenfunction of the Hamiltonian. That means that in order to solve this equation, you actually don't need to find eigenfunctions of the Hamiltonian directive. We need to find eigenfunctions of K. And actually, if you have these two equations, you immediately find, so first of all, from this equation, the H has to be as an operator, it has to be a function of the operator K, and this function can be found by this condition. This is a simple calculation with just two lines, which I don't demonstrate here, and the result is that this Hamiltonian is written by Caspar anomalous dimensions times the logarithm of the generator of the special conformal transformation. That's exact statement in the orders of perturbation theory, and as I emphasize again, in a true QCD. So if you have the generator in QCD, you just have to find logarithm of operator. It's a bit tricky business, but this is exact statement. The constant is undetermined because it is a basically differential equation. This constant can be determined and so on. So and then you can use it to find the equation immediately. So one loop order. That's if you want to find the eigenfunction of this operator, this operator is just the first order differential operator. So eigenfunctions are just that. It's simple. In position space, in momentum space, what happened that instead of the essentially the coordinates are replaced by derivatives, right? And then if you have z squared here, it will produce two powers of derivative. That's why working with conformal symmetry is much easier in position space, because this is a first order differential operator, but in momentum space it's second order differential operator. But this is just different representations of the same operator. And so in the position space, this solution is just that. In momentum space, the second order differential equation is the Bessel equation. So this is the odd function that appears. And then the eigenvalues are the trivially calculated, which is just a anomalous dimension. We just apply this h to this function. So h is just k, and k is replaced by this s. And that's what you get for the result. That's it. To one loop. To two loops, you should work a bit. But the structure of this formula is also such that this gamma cast starts with a coupling. So in order to have two loop evolution equation for the function, you only need to know one loop result for k, which is very simple. We actually have two loop results for k. So we can obtain this H to 3 loops, which we didn't do because at this point it seems that it's not necessary. It's not completely straightforward. We have to work a little bit. But in principle, we can do it to 3 loops. We did it to 2 loops. The situations are relatively simple. So now I'm going to do this another completely other issue is this question of kinematic power corrections in off-forward reaction. So an off-forward reaction is a standard example nowadays is what is called the deep reversal photon scattering. When you have electron scattering from a proton, and in the final state you have a real photon and also a proton. This is an exclusive reaction. There are no other particle produced. And so this it is a virtual photon and this is a real photon. So the point is, since there is some momentum transfer in the T region, then these four momenta are not collinear. So if you want to separate the longitudinal and transverse planes, this is not unique. In deep and elastic scattering, there is a natural separation of longitudinal and transverse distance because of a scattering plane. And you say there's a longitudinal direction, and then you have transverse plane to the scattering direction. This is you call the transverse direction. In this case, this is ambiguous. You can take either combination of because no momenta are not coplanar in 4 dimensions. You can take either two of them to define a longitudinal plane or transverse plane, and the results of your calculation will actually be ambiguous. If you take what we call the leading twist calculation, the results will simply depend on the reference frame. You simply violate by making a leading twist approximation. We violate Lorentz invariance, and actually you also violate word identities, which is a more subtle issue, but word identities will also be violated. And this it has to be repeated by the power suppressed contributions, which will be order of the momentum transfer T divided by your path scale Q, which is virtuality of the photon, and also mass terms in principle, mass correction proportional to the mass of the photon, but this actually not so important. They can be called kinematic because they don't involve new non-perturbative corrections. They can be factorize them, but and numerical, these corrections are actually quite large. So we have invented a method to do this calculation. These 4 QSA. I use it, if you wish, more traditional QCD methods 10 years ago. And recently we did the same calculation in a very different way, applying these techniques which are more directly related to conformal field theory. This can then be done to all this, and then this actually finite paper is written in preparation, but actually it appeared 2 days ago. It appeared on Wednesday in the archive. So this is now, because that is finished. It took quite some time because of the numerics actually. So why the problem is interesting and complicated? So schematically, what you do, you have an operator product expansion, and you have this twist two operators. That's what we did with two approximate. And then you have contributions of operators involving total derivatives. So total derivatives can be involved in several possible ways. For example, you can have divergence in mathematical sense when you contract one index of the Lorentz index on the derivative with index on the operator, or you just can put factors of d squared, so you can do 2 different ways. In addition, of course, you have some other operators which are genome twist 3 or 4 operators, which include, for example, extra gluon fields. This I'm not going to consider. They are irrelevant for the problem that we're considering now. If you have a process like deep and elastic scattering, all these contributions are 0 because the derivative acting operator produces you the difference between the moment in outgoing power. So this is don't contribute. But in off-forward reactions, all these operators have to be considered, and in principle, so these contributors have to be summed up. At first sight, there's no problem. We know how to calculate contributions of coefficient functions of operators. in low orders of perturbation theory, it seems to be that there is no problem to do that. 3-level. But the problem is that the matrix elements of the operators of this type vanish on free quarks. So you can't calculate the coefficient functions comparing the calculation of the amplitude to the matrix element, which is the canonical method. So example is that if you just have the contribution of the operator, which is simply non-singular part of the energy momentum tensor, then the divergence of this operator is given by the quark and the quark-gluon operator with additional coupling constant. Here. So you see that it vanishes in free theory. And then, so the point is that this operator you have to include. It certainly contributes to a problem, but there is a lot of other operators, including quark and the gluon field. And the question is how I want to separate what you need from something that you don't need. And the standard way to do it would be that you simply write the basis of all of these operators, including the quark and the gluon. You solve randomization group equation for this operator. You find that one of these solutions of this randomization group equation has this structure, so it has an almost dimension the same as in leading twist, and you throw away the rest. But it's impossible to do because you can't solve evolution equations for high twist operators. You can write it, but you cannot solve. But actually, so what we managed to do, so we used also conformal symmetry to find that although we cannot solve the evolution equations for twist for operators, but the evolution kernels for twist operators are in Hermitian under some scalar product, which the root of this is a conformal symmetry. The root of this is a conformal symmetry, and if you know the scalar product, you can do it, but going to high twist to that higher than 4 is impractical because you need to know the basis, at least for this high twist operator. You don't know operator basis, don't twist. But you can do it in a different way. And the way is actually also mentioned here. So if you have this kind of expansion, so you can write this in terms of this coefficient function, which now also depends on the derivative. This formula was written yesterday in one of the talks. And then also, this is actually an old statement by Pirara, Grillo, and Gatto from even before QCD, that you can actually find these coefficients using shadow operator formulas. So this is exactly what we did nowadays. So this case that we actually needed a bit more complicated. So also the answer is written in such a form that we can't really use it for a purpose. We can write it differently. We have vector currents here, but not scalar currents, but this is with the technical details which can be done. So these coefficient functions can be found. So this is what we did. And so in this way we could calculate this 3 Heavisky amplitudes with this process. And the new result, which was using the Brillo-Gatta technique, is this red terms here. And this is directly related to the experiments that are done now. So what is plotted here are new results in first class 12 measurement testing from which is published in 2023. So this is beam schema symmetry. So the effects that we're considering become large when the momentum of T becomes large. So you don't probably see very well these numbers which is here, but this is kind of extreme case where T divided by Q squared is something like about 0.4. So in this case, you see that all these corrections, so the red curve is the full result, and other than this approximation is really a very big correction. So actually you shouldn't go to momentum transfer, which is that big. But if you stay with momentum transfer, which are below 1/4 of Q, then the results of the corrections are reasonable. Numerically, they're basically of the same size as the next two leading order corrections in perturbation theory. So, for example, here you can see what is actually happening. I don't have time to explain in detail what are these different curves here, but these are basically the sizes of these corrections. The difference between this full line, and this orange dots is exactly this fist four terms which are calculated in this way. So here they becomes huge in this case, which actually means that everything goes astray. You cannot go with that. But here they kind of reason. So no, finally, there is an example that actually belongs to Alexei, so he should talk about, he knows more about it. I call it Vladimir correspondence. So we have different physics problems in to consider. So one is jet physics, when you have a lot of massless particles essentially, which are originated at one point in space. And in this case, they of course interact with gluons, and they, because of this diagram has ultraviolet divergences, and it is well known that how to treat this divergence. You have this normalization factors for this operator. Another thing, you can have this multi-particle interaction. For example, when you have a lot of particles flying in the same light direction, so they will be fixed transverse distances along the same light like. And then if the exchange go on, if the transverse distance is fixed, there will be no divergences, but there will be divergences because basically the time of this interaction can be arbitrary, and these are known as rapidity divergence. So the point is that these geometries are related by a conformal transformation by some special type, and as a consequence of this relation, the soft anomalous dimensions which appear here and rapidity anomalous dimensions that appear here are related in such a way that they at a critical point they are just the same. And going in rapidity divergences to the real QCD, you have to include corrections from going from epsilon critical to zero, which implies that you have correction proportional to the beta function by the criticality condition, because epsilon is related to the beta function. Epsilon critical is just the beta function times alpha. So this is checked to next to Levinon, and actually it gives well, I think the interesting point here is not so much that you can there is this relation, but this probably gives you an idea that one can prove this factorization to orders for this kind of objects, which I think is not yet completely proven, because the realization of this object is kind of standard, and this, at least in some scheme, is they're related, so you just automatically have the proof that you have factorization to orders. So far, well, Alexei knows better, but my understanding it was kind of checked that it works, but I'm not sure if the proof exists there.
They use it to compute full expression.
Yes. Yeah. So, well, to summarize, basically, I just my main points that QCD in 4 dimensions and conformal QCD in 4 minus 2 epsilon and finely tuned coupling have the same randomization group equation in a Wetzbar scheme, and the difference terms can be expanded in terms of the QCD beta function. This additional term can be calculated to next mechanism. So what was done so far, so what we have to do, so what you can do, you can get off forward evolution kernel from forward randomization kernel with additional n-1 loop computation. So you have basically anomalous dimensions, and then you get the full kernels and with additional computation, which has 1 loop less. You can get off forward from forward coefficient functions up to terms proportional to the beta function, and we have now a couple of papers where we show how to calculate these additional terms, at least to 2 loop order. But there is this application to kinematic power corrections in off forward hard process, which is in the last our formulation is directly related to this classical results in conformal field series, is classical covariant construction. There are this realization group equation for heavy light systems that I have demonstrated, and there is in principle many other applications which I cannot Now, one point probably which I didn't discuss, but let me say a couple of words about complete integrability. So complete integrability is the first hint for complete integrability in QCD. It was actually present in the paper of Ahmed Ali, Gudrun Hill, and myself in 1990, where we found that the recommendation group equation for coordinate gluon operator, so it's basically three particle quantum mechanical problem, we could find exactly the lowest enormous dimension descriptor. Exactly. And we understood immediately that there should be some mathematical structure, but we were not able to find this mathematical structure beyond that. But it was actually the first time when this hints appeared. Then there was this story with Reggie limit, and also there was also discussion of QCD, which I don't want to discuss. But then so we eventually understood that this how this works, so that this feature was related to integrability. This is a paper by Manashov, Derdechov, and myself, and then we used it. So how we used it so far? So we used it to solve renormalization group equation for the barrel distribution amplitude solidities. We used it to solve renormalization equation for the what is called structure function G2. These are the renormalization group equations for coordinate gluon operators. And recently, much more recent, for this all stuff, we understood that they produced some nice results also for heavy light systems. So what happens? So this is what we call heavy light reduction. What happens essentially if you have a heavy quark, then of course the conformal symmetry doesn't exist for mass term. However, if the mass of the quark becomes very large, then it becomes irrelevant to the dynamics of the problem. In the same way as if the quark mass becomes very small, it also becomes irrelevant for the dynamics of the problem. And then essentially the heavy quark mass disappears. So what happens from the viewpoint of a standard ideology of the integrable system, which is basically spin chains, you take one spin to be very heavy. So you just hold one spin by hands, and then you consider the system with other spins, with other spin. So this way, one can really explicitly solve renormalization group equation for systems involving one heavy and two light fields. Actually ABA doesn't really work in this case, and we use these techniques due to Slannon, which is this separation of variable techniques, and so there are really explicit solutions. So it's nice. ABA does give you some. Here you have explicit analytic solution for this evolution equation. So this is and interesting maybe for the integrability community. These integrable models that arise in this way are kind of a little bit non-standard. Usually the Hamiltonian that you get in integrable models is related to the trace of the transfer matrix. You have A, B, C, D transfer matrix, and the Hamiltonian is usually the sum A plus D. So in this case, the Hamiltonian is B or C. The B and C are related by the summation doesn't matter. But so there's a kind of non-standard integrable model. So this is might be integral interesting in this case. Yeah, so that's basically yeah. And then as far as the first directions there are many things that can be done. I think the most interesting for me would be the following. So in order to so in QCD we're dealing with amplitudes. The result of conformal field series are mainly written for the relation function of local operators. So what we do, we expand everything in local operators, we use these techniques, and then we suffer to get back to the level of amplitude. These steps going to local operators and the back is clearly not necessary in principle. It should be possible to do it directly in terms of amplitudes. And mathematically, this is probably the thing is that if you go from representation of the discrete series of, for example, let's say to our group, if we go to representation of the continuous series, that's essentially what we would like to do. And so maybe that would be, so this would be light, a kind of light ray operator, so it's complex spin or something like that, that would produce this kind of result. So, for example, this Polyakov triangle formula, which you know for local operators, is probably also valid for, because it is basically comes from algebra. It's probably valid for the creation functions of involving this continuous presentation. So this is something I think that if it can be done, it can very considerably simplify this this calculation things because we see from the calculation that our final results are usually much shorter than what we get in intermediate step. That's usually a bad thing. You don't do something very important. There should be some way to simplify. So this is my the
Thank you. Have to be a quick exam. Can you share the any questions? Are there any questions?
At some moment, you talk about operators in position space and momentum space.
Yeah.
In which in position space we have one first order differential equation, in the momentum space second order differential equation. So what happens with integration functions? Because in position space you have one integration, which I understand that, but when you have two in momentum space, how do you fix second one? I mean, the amount of information should be same, no?
Okay, so I think that so the point is that this is the formula which is valid on the operator level. And it was once constant. This is a constant that after that everything is fixed essentially. So if you go this and this function of the operator always fixed without constant, just fixed. You simply substitute this operator in the one representation by the operator in a different representation. Don't need anything else. There is no additional uncertainties. There is no additional uncertainties.
Let's say if I would be stupid and I will just solve this equation order by order.
No, I understand the question. I cannot, say, but it is better you should just take this solution and make it for yourself. Yeah, but it's
Because I very,
Yeah, no,
sometimes
this is-
I've
yeah.
seen it in other cases,
Yeah.
where once you transform to momentum space and
Yeah.
start to solve something, indeed you have problems with boundary terms, which you don't know how to fix. And I was wondering, so maybe it's something related here.
no, you see, we usually work in position space,
Exactly.
and therefore, and if you have a result in position space, you simply make a Fourier transform. And this procedure doesn't involve any ambiguity.
No,
So I
no,
said,
exactly here, usually you have some ambiguity, how you fix it, because you don't know what your fields are, and then you have to fix, for example, some boundary conditions, infinity or something like this. Just in order to be able to take your Fourier transform. My question is basically, is it related, could it be related to this or not?
no, well, I suspect that here this will be no ambiguity because ambiguity will be just a polynomial, just a linear function, okay? Essentially, and then it's you just you can you basically have boundary conditions on infinity. You have boundary conditions infinity, which you just don't allow you to add. You know, you have some function which has to behave with some infinities, and then okay, I didn't think about it, but this is probably boundary conditions. Yeah, so because you also of course have this yacht, but you can also k functions. Yes. You have other basic function, but you have to take functions.
So I think there's a question from Joao. Joao, you can unmute yourself and ask.
Okay, thank you. So here, one of the key ideas is considering this conformal field theory at d equals 4 minus epsilon. But there's also some speculation that this theory actually exists in d equals 5, that you have a conformal field theory, just even with pure glue. You can even not consider any quarks, just pure Young Mills, continued in dimension, this fixed point that you found to 5 dimensions. I don't know if you have any intuition or anything to say about that.
Okay, I have no intuition. That's simple. But the point is that actually not only d equal to 5, so people consider this series in the d minus 4 minus something or plus something dimensions are interesting also for for condensed matter community. For example, you want to go from D to 4 to D to 3 by some epsilon expansion or something like that. And then the question is that is in all this situation, epsilon has to be for the 1, right? So you go to 4 to 5, epsilon is equal to 1. So we are working strictly in the perturbative regime. Our epsilon is for the alpha, which is a coupling constant. So when I say that we can prove the conformal symmetry, this is in a weak coupling regime. So epsilon is a small number. By the criticality condition, it is just for the alpha. The criticality condition is simply that epsilon is equal to beta function times alpha, essentially. There's a number times alpha. And if you wanted to go to to epsilon 5, then to epsilon 1, no, then actually I don't know what the action of the theory is, because you can have some other operators appearing. So it's a complicated problem. It's a complicated problem. I think mostly it is discussed from going to between 3 and 4, but it's a complicated problem, I think. So, but I want to emphasize that what we do essentially is a little bit different from what was discussed before, because we don't try to do any non-perturbative physics. We don't try to solve non-perturbative QCD. We use it as a calculational tool for perturbative quantities in perturbation theory for hard processes. Yeah, for hard processes. This is a moderate goal, but this is what we try to do, and we see that it is just technically advantageous. So this is what we basically want to do. So we were able to derive some results that were not possible to derive another way, or maybe possible, but in a much more complicated way. So we view it as a technical tool to do this calculation. The same with integrability. We don't want to use integrability to solve non-perturbative QCD. We just tried. So we always work in a weak coupling limit. That's what we're doing. Of course, I'm not saying that non-perturbative equations are unimportant. They're important, but here we can say much. Here we can. And this theory is actually quite pathological, as I say, that we're considering, because it is not unitary. So on a non-perturbative level, a relation between QCD and this is not unitary. And in order to have a stable saddle point, you have actually to go to larger nerve. So it's not unitary, it doesn't have asymptotic freedom. So it is rather.
May I ask you a follow-up? So how does, for example, supersymmetric QCD fits into so somehow you're using epsilon as a deformation parameter to access some other data and then re-expand. So, but you could think of turning on other deformation parameter. I don't know, like a number of flavors, for example.
Yeah, no,
So,
another possibility. I agree that the general idea is clear. You consider a more general theory. Okay, which theory you consider? There are plenty of possibilities. In principle, many possibilities, and then. I think there are two conditions. First, in this general theory, you want to be able to calculate to some accuracy, and then you should have a way to go back to the theory you're interested in. Yes, and then, for example, if you want to go to n equal to 4 super mills, there is just a very long way to go. You just fix some terms, but there is simply too many things to do. This is the idea which we find reasonable, because these calculations in practice, you always do calculations with in dimensional organization, retaining in terms of all the epsilon that I needed to have, so you basically don't miss out. Another possibility might be, as you actually mentioned, that you can fine-tune number of flavors in such a way that the beta function vanishes. Then you will have a number of flavors just as a function of the number of colors. And you will have also conformal theory. The question is then how you go back. So we don't want to have a theory with this amount of flavors. How you go to a different number of flavors. It is true that what the idea that people are considering, that to consider theory when you just include Fermions, not necessarily symmetric theory, but include the Fermions in different color representations. And then you can disentangle terms which are proportional to an F and the number of these extra Fermions, and then you try to do something. It was, I think, never implemented in a consistent way.
I see.
This was never implemented in a consistent way, but maybe it is possible. Maybe it's possible. Some calculations, I think, People don't write it in this way, but I think that's what they actually do. It exists. There was papers by Mikhailov and some other people who did to do it. But in principle, yes, there are other problems.
Are there any questions for Volodya?
I think I received a question by email at some point, maybe it was from you, whether we know how to use conformal blocks. That is no, we thought about it, but so far we didn't find an example where we could use that.
No, but for example, in the slide that where you have you construct the OP of the two currents, that you can use it afterwards, right? If you look at the 4-point function of 4 currents, then
We are, we are coming from a pragmatical point of view. There is a logical question that we can address. If we consider amplitudes, then no, okay, that has to find a particular. So far, we just didn't find. We of course are aware of the fact that these things exist. They claim for control, but so far we were not able to use that. But to say, from my point of view, a more urgent thing is to find this continual representation. So this is, I think, more.
Other more questions? So then, thank you again.
as you wish.
Okay, I guess we are going to resume at. I guess we are going to resume at in 1 hour and a
Yes.
half, right? Okay.
So I mean, in the discussion session, we can have more questions. I don't know if I'm not sure the question of Joe was answered. Yeah, in the discussion session.